Welcome to 4.4, the Fundamental Theorem of Calculus, Day 1. So we're going to look at how to evaluate definite integrals, and that's what the Fundamental Theorem of Calculus is all about. All right, so that theorem says if a function is, and keyword here, continuous on the closed interval a, b, and f, big F, is an antiderivative of little f, so little f is the derivative, on the interval, on that closed interval, then we have the integral from a to b of this derivative f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay, and we'll go through examples of how this exactly works. You'll pick up on it. Another key point is something called the Net Change Theorem, which takes this fundamental theorem of calculus and just kind of talks about it a little differently. So this f prime, that's the derivative, right? We call that our rate. And this f of b is the end amount, where the f of a is our start amount. Or we can talk about it as the end amount is equal to the start amount plus the integral of our rate. Okay, so that's going to play a nice role throughout the year as well. So make sure we're familiar with the net change theorem. These diagrams just kind of give you a visual of different aspects that we've been talking about. So if we have our curve, here's our secant line. Okay, here's our tangent line, and then we're going to get into area. So we have the area of our rectangle, but then what our integrals are going to get into is the area under these curves. Okay, and that's what this fundamental theorem of calculus is going to allow us to do, is to accurately find the area under a curve. We won't have to find those lower sums or upper sums anymore. So let's look at this first example, where I want you to use the graph that's given to determine whether the integral from -2 to 2 of that y value, x times the square root of 2 minus x, is positive, negative, or 0. So remember, the integral represents the area under the curve, or simply the area between the curve and the x-axis. So I highlighted this portion of our area in red. Why? Because that is the area between our curve and the x-axis that is below the x-axis. So this part is a negative area, whereas I highlighted this portion in green because it is above that x-axis. So if you were just looking at the overall area under this curve, would you say it's positive, negative, or 0? Is there more here? Is there more area in this region, or are they about the same? Do they cancel each other out? And hopefully you recognize there's certainly more in the negative region. So I would guess that in the end, the area will be negative here. Okay, now we're going to get into an example where we're going to evaluate a definite integral. So remember, those definite integrals have those limits here, those limit endpoints. Okay, so this integral should look familiar to us. Now, instead of using the limit definition to find this integral, we're going to actually use the fundamental theorem of calculus. So we can go ahead and integrate this function here. All right, and when we do, we get 2x cubed over 3 plus 2x squared minus 7x. Now the new part of it is we are going to evaluate it, that's what this line indicates, on our interval from 2 to 5. So this is our b value, 2 is our a value, and now we have to take into account f of b minus f of a. So we plug in that b value in for x, and then we subtract, and we're going to plug that a value in for x. And now when we clean everything up, you can see what we get. And as you work through it, just make sure that you get 99 for your final answer. Okay? This next example, I want you to work through on your own, and we'll talk about how we can use our calculator to verify this in class. So don't worry about this aspect of it for the video. I'm going to give you a little hint. When we're taking the integral from -2 to 1 of this function, let's break up this guy as u cubed over u squared minus 1 over u squared. So when you do that, your first line, and then you can break it up into two separate integrals, okay? And now I want you to go ahead and evaluate it, try it, come back and see how you did. Okay, so how'd you do? Did you get what I got? So after we break it up, we can, because we're subtracting two different functions here, we can break it up to two different integrals. So we integrate u du to be 1/2 u squared, and we're going to evaluate it on our interval. We're going to subtract, integrating u to the -2, we get -u to the -1, and again we're integrating that or evaluating that on our interval. And you can see as we work through it, we end up getting 0 in the end. However, there's more to this problem. This is wrong. Why? Why is this wrong? Well, one thing we have to note is that this function, this u cubed minus 1 over u squared, is not continuous on our interval from -2 to 1. It's not continuous when u equals 0. So therefore, at this point in time, we cannot integrate this on this interval. All right, so yes, hopefully you were able to get 0, but then again, we have to look carefully and we have to make sure that our function is continuous on that interval. That's the first part of the fundamental theorem of calculus. Okay, this next example, we're going to evaluate another definite integral. If we have our function 3 minus the absolute value of x minus 3, and we were to graph that from 1 to 4, right? We would have our endpoint when x is 1, we get y to be 1, and we would keep going through and get those points. But because we've got this absolute value, we have to do our little side note, and we have to remember this situation over here. So remember, the absolute value of x equals x when x is greater than 0. And the absolute value of x equals the opposite of x when x is less than 0. So meaning what's inside is either greater than 0 or less than 0. Okay? So now we're looking at the absolute value of x minus 3. Well, the absolute value of x minus 3 equals x minus 3 when x is greater than 3, because that means inside is positive. Okay? The absolute value of x minus 3 equals the opposite of x minus 3 when x is less than 3. So when x is less than 3, we get a negative value inside of the absolute value. So we have to take the opposite of that. And then just note that x minus 3 equals 0 when x equals 3. So this is kind of our breaking point when we're going to break up our integral into two separate integrals. Okay, so we have to use these as our breaking point. So instead of the integral from 1 to 4, I'm going to break it up into two separate integrals. The first integral goes from 1 to 3, okay, and this is going to be when our x values are 1 to 3, or simply less than 3, then the absolute value of x minus 3 is really equal to the opposite of x minus 3, okay? Then we're going to add that, and we have to fill out the rest of our interval. So now our next integral is going to go from 3 to 4, and from 3 to 4, the absolute value of x minus 3 equals x minus 3, because x will be greater than 3 at this point. So now we have our two integrals that we can certainly clean up and integrate. And when we clean up this first integral, we're left with just the integral from 1 to 3 of x. And when we clean this integral up, we're left with the integral from 3 to 4 of 6 minus x. Now we can go ahead and find the antiderivatives, okay? And we're going to make sure that we evaluate each of those pieces on the correct interval. Notice this one is from 1 to 3, and this is from 3 to 4. So as we go through and we're plugging in those x values, verify that this is what you're getting, and in the end, you should get your ultimate answer to be 6.5. This last example we are going to integrate from 1 to 3 the absolute value of x squared minus 4. So just like before, I do my little side note. The absolute value of x squared minus 4 is equal to the opposite of x squared minus 4 when x is less than 2. And the absolute value of x squared minus 4 equals x squared minus 4 when x is bigger than 2. So it equals 0 when x equals 2. So this is when x equals 2, that's kind of our breaking point for our interval. Okay, so keep this in mind. Now, before we go ahead and integrate this, let's just look at the graph itself. If we were to just graph the absolute value of x squared minus 4, forget that. If we were going to just graph x squared minus 4, right, what would that look like? Well, it would be this parabola with the vertex at 0, -4, and we would continue on here, right? However, we're graphing the absolute value of that. So this portion below would then turn to positive, okay? So that might also help us figure out our intervals and whether or not the absolute value of x squared minus 4 equals x squared minus 4 or the opposite of x squared minus 4. Now we're also given the interval from 1 to 3. So we're finding the area of this piece and we're going to add it to the area of this piece. Sometimes having the diagram will allow you to set up your two integrals with the correct intervals. So I want you to give this problem a try with how we came up with the values for the absolute value of x squared minus 4. Give it a try, pause the video now, come back and let's check on each other. Okay, so you should have set up two integrals, one from 1 to 2 of the opposite of x squared minus 4 dx, plus the integral from 2 to 3 of x squared minus 4 dx. When you integrate it, this is what you will get. Watch your signs, and you're going to integrate from 1 to 2 for this first antiderivative, and then from 2 to 3 of the second antiderivative. So as you go through and you plug everything in, you should get a final answer of 4. If you have any questions on this video, make sure to ask because this is a very, very important topic moving forward.